is meant to quickly review the concepts and the mathematics skills that were learned in units 8.1 through 8.4, which is the mole and stoichiometry. So let's begin with talking about moles and molar conversions. We're not going to spend too much time talking about the concept of a mole, but we're going to spend this review practicing the conversion skills that you learned. So if we remember that there was a mole roadmap, which helps you keep track of where you are in the problem, we have this map centered around the mole, meaning if you have a quantity in and the unit is moles, that means you're starting here at the center of the map. Now we can convert to mass of a substance in grams. And if you are trying to convert a number that is in moles and you're trying to convert it into mass, what you will need to use in your conversion fraction is the equality that 1 mole is equal to the molar mass. And of course, the molar mass is just the atomic number, or I'm sorry, the atomic mass from the periodic table. And we'll talk about how that is set up in the conversion fractions momentarily. Other units that you can be converting to from the mole is particles. So if the problem is asking you something about molecules or atoms or formula units or even ions, you would use the conversion or the equality of 1 mole is equal to Avogadro's number 6.02 times 10 to the 23rd. There is another conversion that we touched on that we will be talking about. We haven't really learned too much about gases, but we can convert to volume of a gas, not plural, volume of a gas. And that unit would be in liters. And this is only valid to use this if the gas is at standard temperature and pressure. And all the problems at this point will be in standard temperature and pressure. When we get to the gas unit, we'll have non-STP problems. But for now, the conversion equality that you would use is 1 mole of any gas at STP will have a volume of 22.4 liters. All right, so that is the map that'll help you with the conversion problems that are here for you to practice. So a sample of carbon dioxide weighs 640 grams. How many moles is this, right? So you have a given quantity and you're being asked to solve for something else. It may be helpful to know what the substance is. You only really need to know what the substance is if you are converting to anything to mass. If you're converting to particles, it does not matter what the substance is. This equality here is irrelevant for the identity of the substance. Same for converting to volume. This can be any gas. So the only conversion where you have to know the formula is mass to mole. So remember how we set these problems up. You start with the given quantity. In this case, it's 641 grams of CO2. We want grams of CO2 to cancel, and we want to convert to moles of CO2. And so if we are looking at our map up here, we're given a quantity in grams, and we are being asked, we're given grams and we're being asked to solve for moles. So that means our conversion fraction, this thing right here, needs to use the equality of 1 mole is equal to the molar mass. So remember, it's always 1 mole. You're always going to be 1 with the mole in these problems. For the mass of CO2, we need to consult the periodic table for the formula CO2. So carbon, single carbon is 12.0. And 2 oxygens, each at 16.0. We add all that together, so 12 plus 32 is going to give us 44.0. All right, so this sets up the problem. Remember, grams over grams is going to cancel. Moles of CO2 is going to be what we have left over. Then it just comes down for you to do the math of 641 divided by 44. Okay, so I'm not going to do the math here. I'm just going to leave it set up for you to check your work. And I'll have the answer key posted in class. Next question. A sample of iron contains 2.93 times 10 to the 26 atoms. So that is a given quantity. How much will it weigh in grams? So we're given particles and we are being asked to find mass. So going up to our map, we are given a number specifically in atoms, but that's a particle, and we're being asked to convert it to mass. That means we're going to need to use two conversion fractions. We're going to need to use Avogadro's number in the first fraction, and we'll need to use molar mass in the second fraction. So let's set it up. So 2.93 times 10 to the 26 atoms of Fe, that's iron. Putting that in the start of our fraction. I want atoms of Fe to cancel, so I'm going to put that unit in my denominator, so atoms of Fe. And if you like using the map, right, we're going from atoms to moles. So we are going to need to use 1 mole and 6.02 times 10 to the 23 particles. So that's going to be the number, the Avogadro's number is in our denominator here. And 1 mole up in the numerator. If I stop here, atoms of Fe are going to cancel, and you will be left with moles of Fe. Remember, we are trying to get to grams, not moles, so we have one more fraction to set up. Since I want moles to cancel, I will now put it in the denominator, and I will put grams of Fe in the numerator. When you set up these numbers, it's always 1 with the mole. And when you're figuring out how many grams are in 1 mole, you use the periodic table. To the nearest tenth, it looks like that is 55.8. Moles of Fe will cancel. Your unit that is left over will be in grams of Fe. Multiply by anything in the numerator, divide by any number that is in the denominator. All right. One more, if you're looking to check one more. If you have 3.5 liters of sulfur hexafluoride, how many moles do you have? So we are given liters, which is volume, and we are being asked to solve for moles. So if we look at our map, we are given liters, and we are being asked to solve for moles. We only need the equality of 1 mole equals 22.4 liters, so we do not need to look up the molar mass. If we did, sulfur hexafluoride, you'd have to translate that into a formula. Because we see a prefix here, we know that the formula is telling, the name is telling us the formula. So sulfur is S, fluoride is F. There's no prefix in front of the sulfur, so that's just a 1. Hex is 6. So that would be the formula if we needed it, but we don't. So 3.5 liters. I'm going to go ahead and put it in anyway because I like to be very clear in my labels. So 3.5 liters of SF6. I want liters of SF6 to cancel, and I'm going to convert it to moles of SF6. 1 mole is equal to 22.4 liters. Liters of SF6 cancels with liters of SF6. And there you go. There's the setup for your problem. Okay, so that is basically all the conversions that we learned so far in units 8.1 and 8.2. Let's take a look at what we learned in 8.3, which is percent composition, and a couple different ways that these problems can be asked. What is the percent by mass of carbon in glucose? So, you know, percent composition, basically you are looking for the general equation of percent composition is the mass of the element over the mass of the compound. And then, of course, you have to multiply the whole thing by 100 to put it into percent form. So that is sort of the generic, that'll tell you the percent by mass of the element in the compound. So you just need to figure out how you're going to get those numbers. If we only give you a chemical formula and no grams, no values of mass here, you're going to have to use the periodic table to get the masses of each element. So let's take a look. Percent by mass of carbon. So we are only looking to do a percent for carbon. Sometimes you'll be asked to do like the percentage for each of the 3 elements, but this problem is just asking us for carbon, so that's the only one we're going to focus on. So what we need is the mass of all the carbon in this compound, and there's 6 of them. So each carbon from the periodic table is 12.0. 6 times 12.0, if you're not good at your 12s times tables, it is 72 grams. So 72 grams of carbon, that's 6 times 12. But now, so that's the mass of the carbon, we need to find the mass of the whole element. So we just found out that those 6 carbons weighs about 72. There's 12 hydrogens, each at 1.01. So 1.01 times 12 is going to give us 12.12. And 6 oxygens, each at 16. And I'm getting that 16 from the periodic table. So that's going to give us 96. So 96.0 plus 12.112 plus 72. So the mass of this entire compound is, what's a little light glare there, 180.12. So that's the mass of the whole compound. And I'm not really being too mindful of my significant figures here. I suppose I should have had 72.0 in my numerator. Both the numerator and the denominator have grams, so those are going to cancel. I want to multiply this whole thing by 100 to get it into percent form. So let's take a look here. Quite a bit of glare from that light. Apologies. Okay, so let's take a look. We're going to have 72, and we're going to divide that by 180.12, and we get, all right, let's try that again. A little math typing error. 72 divided by 180.12 equals times 100 to put it in that percent form. And let's go with 3 sig figs here, 39.9. Oh, but that 7 rounds up the 9. So this is going to give me 40.0% carbon. So that's all we need to do for that problem, just using the molar masses. All right, let's take a look at this next one. You have 95.2 gram sample of the compound, so there's your compound mass. There's only 2 elements, there's carbon and oxygen. They're giving us the mass of the carbon, they're giving us the mass of the oxygen, so here they're giving us all the masses. What's the percent composition of the elements? So that means we're meant to set up the percent of carbon and the percent of oxygen. And since they gave us the masses straight away, you just need to keep track of everything, right? Mass of carbon is 40.8 grams, divided by the whole compound of 95.2 grams, multiplied by 100. Grams cancel. You can get your answer from there. The oxygen, they give us the mass at 54.4 grams, divided by the mass of the whole compound, multiplied by 100. That's how you set up that problem. Okay, I'm going to move on. I'm going to assume that you can finish that problem, but that's the reminder of how to set those up. Okay, now in this next problem, you're going to have to do a little bit more digging. They give you a sample of a compound. So the compound has this entire mass. That's the compound mass. There are 2 elements, oxygen and fluorine. The sample contains 0.128 grams of oxygen, but we are being asked to find the percent composition of, I guess, both elements in the compound. So that means we need to find percent oxygen and we need to find percent fluorine. So we know the compound mass is 0.432 grams. 0.432 grams. So I'm going to set those up for both of my compounds. They're telling us the mass of the oxygen is 0.128 grams. All right, and so there's a couple different ways you could do this. Because the compound contains only fluorine and oxygen, remember conservation of mass, element plus the element equals the compound, right? And so if the compound is 0.432 grams, and we know that one of the elements is 0.128, then we can easily figure out what that X would have to be, what that other element mass would have to be. So 0.432 minus 0.128. And so we know that this has to be 0.304. So that's going to be the mass of the fluorine, and that's how you would set that up. Okay. So I'm going to leave those answers for you to calculate, but that's the basic setup. And let's take a look at our the most recent section of the unit, empirical and molecular formulas. Lucite, which is plexiglass, it's a polymer that contains these percentages of these three elements, carbon, hydrogen, and oxygen. What is the empirical formula? So remember, empirical formula is a formula of some number of carbons to some number of hydrogens to some number of oxygens. And remember, those subscripts are mole ratios. So we have to take these percentages and convert them into moles and get a mole ratio to make that formula. So best thing you can do is keep yourself organized, make a line for carbon, a line for hydrogen, a line for oxygen. When you, what we need to do, remember, turning percentages into moles, but because these are percent by mass, if you had a 100-gram sample of this substance, you would have 59.9 grams of carbon, you would have 8.06 grams of hydrogen, and 32.0 grams of oxygen. So just swapping out the percentage for grams gets you ready to go. So remember, we're going to convert mass to moles as our first step. So I'm going to write a little small so I can fit this in. So 59.9 grams of carbon. This is where you want to set up your conversion bracket. And we're going to convert grams of moles into moles. Oh, sorry. We're going to convert grams of carbon into moles of carbon. So 1 mole of carbon from the periodic table. Never have my periodic table too far, right? 1 mole of carbon weighs 12.0 grams. All right, and I'm going to go ahead and set that problem up. 59.9 divided by 12, and I'm going to get 4.99 moles. Okay, so leave that alone for now. Let's do the hydrogen work. 8.06 grams of hydrogen. I'm going to put grams of hydrogen in the denominator to cancel. 1 mole of hydrogen in the numerator. And from the periodic table, because it's never too far away, 1 mole of hydrogen weighs 1.01 grams. So let's take a look. 8.06 divided by 1.01, you might already be able to see this, that this is coming out to about 7.98 moles. All right, let's do the work for oxygen. We've got 32.0 grams of oxygen. Grams of oxygen in the denominator, 1 mole of oxygen in the numerator. From the periodic table, as you might know, and you probably are starting to memorize these because you see them so often, 1 mole of oxygen is 16.0 grams. And you probably can see, without having to do the calculator, but 32 divided by 16 is going to give you 2 moles. All right. So now that you have these moles, we can see here what we're trying to get is our mole ratio. So to do the mole ratio, I'm going to do carbon, hydrogen, and oxygen. You have to take each one of these mole values, 4.99 for carbon, 7.98 for hydrogen, and 2 for oxygen, And I'm going to divide all of those by the smallest of all three. In this case, it was the number 2 is the smallest of all of those numbers. Okay. And we can see here that this is an unusual problem because I think, yeah, but so 4.99 divided by 2 is, you may be able to see it, but I'll just do it on the calculator just to show you. It comes out to about 2.5. We're going to start doing a little rounding. 7.98 is about 8. Divided by 2 is going to give us 3.99. I'm going to call that 4. And 2 divided by 2 is 1. So here's a situation where we have a 2.5 to 4 to 1 ratio. But the problem with that is that you have to have whole number ratios here. So if you have one of your mole values come out, even after you've divided by the smallest number, if you have it come out as a half, no big deal. You just double everything to maintain the ratio, but that'll put you back into whole numbers. So this becomes 5, this becomes 8, and this becomes 2. So that right there is our empirical formula. All right, the next step for moving on from empirical formulas is if you are being asked to find the molecular formula, right? Because the molecular formula could be the empirical formula. Like the molecular formula might already be the lowest reduced ratio, but sometimes it's not. And so to find the molecular formula, you have to have two things. Number one, you have to be given the empirical formula. And number two, you have to be given the molecular mass. That's number 2, the molecular mass. So to find what we were looking for is a multiple, right? And so if we divide the molecular mass by the empirical mass, we're going to get a multiple. So let's see what that looks like here. The molecular mass here is 96.9. That's given. That's right here, given. The empirical mass, we're going to have to do a little side calculation. We've got CH, and that's a Cl, that's a chlorine. Carbon is about 12. Hydrogen's about 1. I'm going to kind of rough this out. And chlorine from the periodic table is about 35.5. So if we add those up, we get 35.5 plus 12 plus 1. So that's going to give me 48.5. So that mass is going to go in the denominator. And if I divide those, 96.9 divided by 48.5, we get about 2, 1.997. We're going to call that about 2. That's our multiplier. That means the empirical formula, which was 1 to 1 to 1, that was our empirical formula. The multiplier of 2, we just multiply all those subscripts by 2. So this is C2H2Cl2. That is our molecular formula. All right, so that is Unit 8 so far in a nutshell. I hope that you are feeling good. All right, let me know when you have questions, and I will see you back in the classroom.